So we were done with bond neighbor cycle. The next thing is we are going to talk about the enthalpy change of solution. ठीक है, standard enthalpy change of solution. So uh, that's known as delta H solution. Now what happens in this, let me just check, did we try to define what enthalpy of solution was? Just a second. No, I don't think we did that. ठीक है. This is coming back to this. The standard enthalpy change of solution. Do you know what that is? Any idea? Okay, what happens in enthalpy of solution? Lubena, can you hear me?
The enthalpy change that occurs when a solute is dissolved in a solvent under standard conditions.
And exactly 1 mole of solute. So it could be any solute or any substance basically that dissolves in aqueous state to form. It dissolves in water to form. Like ionic compounds would dissociate when they are dissolved Na+1 aqueous or Cl-1 aqueous, which could be written as, this could be written as just NaCl aqueous, right? This is kind of important. Just make sure you know this, because a lot of questions, they try to confuse you with this. Remember, NaCl aqueous and Na+1 aqueous and Cl-1 aqueous, that's the same thing. So as long as 1 mole of a substance is getting dissolved, that is going to be known as the standard enthalpy change of solution. And it could be endo or it could be exo, and it could be any substance. You could have ethanol, for example, C2H5OH, that might be dissolving, and it might dissolve to form. It's originally it's a liquid, so you mix it in water and it turns aqueous. So that would become C2H5OH. Aqueous, right? So as long as 1 mole of a substance is mixed in water and it completely dissolves, that's enthalpy of solution. So the definition is that it's the energy released or it could be absorbed so it's endothermic or exothermic. It could be both, depends. So it could be endo, it could be exo. So energy released or absorbed when 1 mole of a substance completely dissolves in water to form 1 mole of simply completely dissolves in water. That should be it. To form an infinitely dilute solution. Which basically means a dilute solution. And it's supposed to be measured under standard conditions. Okay. So is this clear? What's happening in enthalpy of solution? Lubena, is this clear?
Yes, sir.
So now another thing is, first thing, why is it endo or exo? Why can it be both? Now one thing is that it involves both bond breaking and formation. So both things, bond breaking and formation, are happening. And both things are going on simultaneously, which is why it depends whether bond breaking happens. It requires more energy, then it's endothermic. If bond formation releases more energy, then it's exothermic, because bond breaking is that part is endo, and the formation part is exo. So it's the sum of two processes having different energy signs. So I'm gonna give you an example of what happens when ethanol dissolves. Now, let's say there's a solution and that contains exactly just two molecules of ethanol. So you've got C2H5 and OH. So this is your H. Now, ethanol molecules have intermolecular forces. There's this oxygen with its lone pairs, so it's kind of partial negative. This one is partial positive. And there might be another ethanol molecule which might be aligned with the first one, and they both would be attracted. This oxygen would also have a partial negative lone pair, and the H would be partial positive, and they're going to be attracting each other. Okay, so they're both attracted to each other, and there's this bond, intermolecular force known as hydrogen bonds, between them. And you put ethanol in water. Now, what does water have? Water has H2O molecules, and those water molecules also have hydrogen bonds in between them, because the H is positive and the O has two lone pairs. They have partial negative charge, so they're going to be attracting each other. Okay, is this clear? So,
Yes.
so what's the first thing? When you mix them together, you stir them. Okay, a lot of times stirring is required to mix substances. The purpose of that is you break the old hydrogen bonds. Okay, so what you're trying to do is, and remember, hydrogen bonds are not. Hydrogen bonds. These hydrogen bonds over here and these hydrogen bonds over here, they're kind of different. Because the lone pair over here might have a different partial negative charge compared to the lone pair in water, because they're inherently different molecules. So carbon's electronegativity is going to affect the lone pair density over here. So remember, if all hydrogen bonds are not exactly the same, like ammonia is going to have a different type of hydrogen bond compared to water, compared to HF. Okay, is that point clear as well?
Yes.
So when you stir them, the old hydrogen bonds break, right? So that's your first part. So you're vigorously stirring, and so the first step is old bonds are, or the old attractive forces are broken. So that's endothermic. That is why you need to stir. Anyways, so the molecules kind of realign and they mix up. So there might be a water molecule over here now. Okay, this water molecule, so they kind of get mixed up, right? And now new hydrogen bonds are going to be formed. The lone pair on this oxygen would be attracted to the H, which is positive over here, and they would be attracted to each other. Similarly, the oxygen lone pair over here would be attracted to the H over here, which is partial positive, right? And this thing keeps on repeating. There's another lone pair which is partial negative, and it would be attracted to the H over here. This H, which is partial positive, would be attracted to the oxygen lone pair, and so on. So it's basically new attractive forces are formed. So new bonds are formed. So it kind of depends whether it's going to be endo or exo, based on how much energy is needed to break bonds and how much energy is released during bond formation. Okay, so is this all clear? Ruben, is this clear?
Sir, why do the oxygen have different partial charges?
I said, why do they have different, I'll explain. As I see, you have this oxygen and its lone pairs, right? Okay, let's focus on the lone pairs. And let's say you have a methanol molecule and you have oxygen having lone pairs, right? The thing is, carbon chains have an electron donating effect. Like carbon has a lot of electrons, so it's going to push its electron density slightly, very slightly, towards this oxygen. So what do you think happens to the negative charge on oxygen? It kind of increases. Is that clear?
Yes, sir.
Okay, so I'm just saying that the bonds that are being broken and the bonds that are being formed, even though they are both hydrogen bonds, but they're not exactly the same. They don't have exactly the same strength or the same type of hydrogen bonds. Okay, and the same goes for ammonia. Like the lone pair on ammonia or nitrogen would have a different electron density compared to a lone pair on oxygen. Is that clear?
Yes, sir.
Okay, so remember, even if the atom is the same, uh, there are going to be differences if the molecule is different. Because all the other atoms that are bonded to it, they're going to influence this negative charge over here. Okay, later on when we study organic chemistry, we're going to study this in a lot more detail, because that affects why. I mean, things like this affects why alcohols are not able to lose H plus one ions. Carboxylic acids are able to. Their OH is able to lose H plus one ions. So just remember that even if the atom is the same, the electron density is not always exactly the same. As anyways, coming back to the main point, which was that enthalpy change of solution, if it's overall coming out to be negative, then uh, that means the solute is soluble, and it would be more soluble at lower temperatures. Remember, exothermic processes are more soluble at, not more soluble or more feasible at lower temperatures. Like if you want to convert liquid water into ice, you have to remove energy, and you're able to remove energy at lower temperatures. So, and the second one is if enthalpy change of solution comes out to be endothermic, then that means it's not, I mean, don't use absolute terms. What I basically mean is that the first one is more likely to be soluble, the second one is less likely to be soluble because it needs energy to dissolve. And it would be more soluble at higher temperatures because endothermic processes, they require energy, so they would be more soluble at higher temperatures because that's when you're able to provide it energy. So for example, melting of ice, it needs energy, so it's more feasible at higher temperatures. TK, is this clear as well?
Yes, sir.
And so next, what I'm going to talk about is, we're going to come back to this in a bit, but what we are going to talk about is the standard enthalpy change of hydration. And then we're going to discuss the solubility again. So standard enthalpy change of hydration, which is delta H hydration. Now, what standard enthalpy change of hydration is that it's when 1 mole of gaseous ions, any ions, like Na plus 1 is gaseous, it mixes with water and gets completely surrounded by water to form 1 mole of Na plus 1 aqueous ions. So this is enthalpy change of hydration. and it's always exothermic. So it's always exothermic as bonds are formed only. I'm going to talk about this in detail, just focus on this thing that should be 1 mole. So this is by definition what enthalpy change of hydration is. And it could be any ion, it could be, but remember it's ions that actually turn aqueous. Like if you have Cl ions, then your Cl ions, same thing would happen, Cl minus 1 gaseous, they mix with water and they turn into, they turn into Cl minus 1 aqueous. So this is hydration, and this is something that's going to happen. So I'm just going to make a point. This is only for ions that turn aqueous or that exist in aqueous state. For example, not all ions actually turn aqueous. For example, O minus 2 gaseous ion, you mix it in water, you never actually, it never actually turns O minus 2 aqueous ions. Okay, this particular reaction in reality never actually happens. Do you know why it doesn't happen? Any idea? Have you ever seen O minus 2 aqueous? Lubena, are you there?
Yes, sir.
Acha. So O minus 2 aqueous. I mean, there is, the thing is that there is no O minus 2 aqueous. Actually, O minus 2, what actually happens is that O minus 2 ions, they react with water. They don't dissolve in water, they react with water and they turn into OH minus 1 ions. So that's a chemical reaction taking place. So that's not hydration. You do remember that any oxide like sodium oxide would turn into NaOH. TK, it won't dissociate. It won't, like if you add sodium oxide to water, there is no O minus 2 ion forming, there's NaOH forming. Okay. So is this clear that enthalpy change of hydration is only for those ions that actually turn into aqueous ions? Okay. Clear?
Yes, sir.
Acha, plus, now what happens when an ion is aqueous? Okay. For example, you've got a container and that container has water in it and you've dissolved Na plus 1 ions, aqueous, and you've dissolved NaCl. Let's say you've dissolved Cl minus 1. And the ions are in aqueous state now. And there are lots of water molecules that are everywhere. Okay, and the water molecules are keeping them apart. Okay, so it's a very dilute solution, which means there's plenty of water molecules and there's no way that Na plus 1 and Cl minus 1 would get back together again. Now, our idea of Na plus 1 and Cl minus 1 aqueous so far has been that this Na plus 1 is just randomly floating around. I mean, this is what we think is happening. Okay, they're just randomly moving around inside water and they're just floating around. When in fact, when an ion dissolves in water and turns aqueous, what actually happens is that the ion actually goes and bonds with the water molecules. So if you have Na plus 1, so this is exactly what's going to happen, that Na plus 1 has 6 sides. So it has, so it's got six sides. Okay, there's like if you're in a plus one, there's a top, there's bottom, there's front, back, right, left, right. So there's six sides. And Na is a positive ion. So what it would do is that it won't just float around inside water. What it would do is that water is a polar molecule. So the lone pairs on water are actually going to be attracted to, they're actually going to be attracted to the Na plus one ions. Okay, and they would end up forming a dative bond. So a dative bond or a coordinate bond forms between the solvent and the solute or the ion. Lubena, is this clear?
Yeah.
And there would be water molecules coming from all over the place, from all sides. Most of the time, it's six. And it could be any number of water molecules that would be attracted to the Na plus one. But the number is limited by the space available. Like you can't fit more than six water molecules around Na plus one because you run out of space. So here are our now there's a separate chapter on this, and this is known as a complex ion. This is, I mean, all our lives we said that we talked about Na plus one aqueous, when in fact it's not Na plus one aqueous, it's Na with six water molecules attached to it. And overall the ion has a charge of, plus one. Okay, is this point clear?
Yes, sir.
And the same with pretty much any other ion. Like if you talk about H plus one aqueous, I mean, all your life you've talked about H plus one aqueous. So I'll just give you an idea that in fact there is no H plus one ion in aqueous state. What happens is that a water molecule comes in, and the lone pair of the water molecule is going to attract the H plus one, and it would form a dative bond with it. So the ion, I mean, whatever you call H plus one aqueous, that's actually the hydronium ion, which is H3O plus one. Okay, so there is no H plus one aqueous in reality. Similarly, there is no Na plus one aqueous. So Na plus one aqueous, Cl minus one aqueous, these are all simplifications. So this is what happens when an ion gets hydrated. When we write that there's a gaseous ion simply means that there's an ion that's not bonded to anything, and then you put it in water and it gets completely surrounded by water molecule, forms those dative bonds, which is why this is always exothermic, because bonds are getting formed. So is this point clear?
Yes, sir.
So, and it's always exothermic. So just a second, bonds forming. So when do you think an ion would form stronger bonds? Like, which ions would form stronger bonds?
The ones that have the capacity to form more data.
Nee, but let's talk about, I mean, which bonds are stronger? Smaller atoms make stronger bonds or bigger atoms?
Stronger, smaller atoms.
Okay, so smaller the ion and greater the charge. So that is when they form stronger bonds. So basically, you can say high charge density, that means higher charge density, greater enthalpy of hydration. So delta H hydration would be more exothermic. So it's going to be more exothermic enthalpy change of hydration. Okay, is this point clear as well?
Yes, sir.
And sometimes what happens is that some ions, it's very hard for some ions to actually get hydrated. Like if it's an Al3 plus ion, let me just try and copy paste this. So hydration is when it gets surrounded by water molecules, right? But sometimes, I mean, you've studied in inorganic that some ions they hydrolyze in water, and the reason why that happens is because of that. Like NaCl dissolves, right? NaCl forms or Na ions they always form aqueous ions, right? But if you had Al3 plus, now Al3 plus has a pretty high charge density. So if I have Al3 plus, what eventually happens to Al3 plus is that oxygen doesn't only, I mean, it has a lone pair, it has a partial negative lone pair, and that lone pair is attracted to the Al3 plus ion, right? But at the same time, this oxygen also has an H that is partial positive. So what do you think the Al3 plus would do to it? Al3 plus is going to repel the Al3 plus has a pretty high charge density. It's a very small ion with a very large charge. So it's going to attract the lone pair really strongly, but it's going to at the same time repel the H plus one very strongly as well. Is that clear? So
Yes, sir.
so what it eventually does is that it starts to hydrolyze. It starts reacting with the water molecules, and it rips off the OH ion away from it. I mean, it repels the H plus one and pulls the OH minus one closer to it. So eventually, it ends up forming aluminium hydroxide. Uh, and so so the enthalpy of hydration. I mean, there's going to be a reaction with water instead of actually getting hydrated. Is this point clear as well?
Yes, sir.
So I'm just going to write that there's another problem that is when you have very high charge density, then instead of getting just hydrated or getting surrounded by water molecules, hydrolysis starts to or starts. So instead you get hydrolysis. So just to sum this up, just remember hydration is when an ion gets completely surrounded by water, and that's about it. Okay? Or any ion, positive or negative ion. If it's a negative ion, then it's going to attract the H positive ions to it. And again, a dative bond would be formed, but the dative bond would be in the other direction. It's going to be Cl minus one, and the lone pairs on Cl minus one that would be attracting the that would be attracted to the H positive. ठीक है, clear?
Yes, sir.
So now we are going to talk about. So now we're going to talk about solubility of, and specifically, we will talk about a thermocycle. Let me put the. I mean, thermocycle is a Hess cycle, right? Just like the Born-Haber cycle. So solubility of ionic compounds. If you want to dissolve an ionic compound is Na plus one attracted to Cl minus 1, and that Cl minus 1 is again attracted to Na plus 1, which is then attracted to Cl minus 1. So think of this as a tiny crystal of NaCl. And you have a, let's say you have a bowl of water, and you're going to try and mix it in the water. The first thing is you stir it and you try to break the lattice. Okay, that's the first thing. That's why you stir it. Break the ionic lattice. That's the first part. And you want the Na plus 1 and the Cl minus 1 to dissociate or disperse in solution. Okay, that's the first part. You break the ionic lattice. And second part is the ions then get surrounded by water molecules. Like I showed you. So the second part is you've got molecules that would be ions that would get completely surrounded by water molecules. So this is the negative of lattice energy. Okay, I'm just going to leave it here. Okay, you break the lattice. In lattice energy, you form the lattice from. And the next part is enthalpy change of hydration. Okay, is that clear?
Yes.
Okay, so to dissolve an ionic compound, you have to break the lattice and separate the ions. They would become gaseous ions, which means that they're not bonded to each other anymore. And then they would immediately form bonds with water. They would form new bonds with water, and that would be enthalpy change of hydration. So two steps involved: step one and step two. Okay, we're going to talk about this in the next class then. Okay, Claire, if you do you have any questions?
No, sir.
चलो ठीक है चल ठीक है let's continue next time. Try and do the complete did I send you the bond able cycle worksheet? I think I did.
No.
So try and do the complete worksheet. ठीक है
Sir, you didn't send it to me.
अच्छा I didn't, so I'm sending it right now. ठीक है चलो okay take care. Allah Hafiz.